Are there any questions? Let me share. So I think that during yesterday's quiz, some of you had problems because you had to make an update to responders. So if you want, if someone wants to upload, I kind of changed the settings of that quiz so that you could do it again. So if someone prefers to upload some new solution to the quiz or whatever and retake it, you can do it today, and I was planning on grading them tomorrow, so that wouldn't be a problem. So that's just in case someone wants to, change their solutions or whatever to the quiz. You can still do it since responders was given those problems. The idea is, as I had said yesterday, to finish the material for Monday's exam today. So I'll send you a couple of hours after class, like a review guide and some practice exams for the exam on Monday. But today we'll finish the last topic for the exam. Okay, so we have to talk about related rates. Okay, so what I was saying yesterday, which you can still see on the iPad notes, is that the first derivative of a function gives you useful information on when the function is increasing or decreasing. So if the first derivative was negative at some given point, then you are in the situation that you see here, where like if you think of the graph as some sort of roller coaster, you're going downhill. So your height is decreasing. But if the first derivative is positive at some point, like as the situation that you see here, then again, in this roller coaster analogy, it's like going uphill. So your height is increasing as you pass that point. Okay, so negative derivative has to do with decreasing, and positive derivative has to do with increasing. So that will be useful in a couple of minutes to interpret certain problems about related rates. So, which more or less is just like some applications of the derivatives. It's not like really like a new tool to find derivatives. It's just how to apply derivatives in some more realistic situations. So the other thing I had to tell you before doing some examples of related rates is this thing about other interpretations of the derivative, or so the one that we have been using the most is like the slope of the slope of the tangent line. So again, you had the XY plane, and then you have a curve. And the slope is this line has slope. If this is the point X, this line has slope m equals to f prime of x. Okay, so that's like a useful thing, a useful way to think about the derivative, um, especially if you're dealing with geometric problems, but it's not the only way to think about it. So the more like general conception of a derivative is as an instantaneous rate of change. So let me explain what I mean by that. So if you remember the definition for the derivative, if you had a point x and you, let's see, I don't like this graph, let me change it. Yeah, I think this looks a little bit better. So if you had a point x and you move a little bit like delta x, right? Then the function changes, the values of the function change, right? So for example, here, the function is f of x, and here the function is f of x plus delta x, right? So there is a corresponding change in the function, which we had called before delta f, right? So the definition of the derivative in terms of a limit, if you remember it, is that f prime of x was the limit as delta x approaches 0 of delta f divided by delta x, right? That was one way to write it down, like the limit definition. But what is delta f divided by, like, the important thing now is to think a little bit more about this ratio. So let's try to think about what is this quantity. What does this mean? This means how much delta f changes uh, when you when you change when you vary x by an amount delta x, right? So this is the change of f you get uh, or like, well, I mean, maybe I should put it like this. Delta f, right? Delta f was the change of f you get by by varying by changing x by an amount delta x. So for example, if you if you look at this fraction, you're dividing by delta x. So it's kind of like the fraction itself is kind of like a change per unit of x. It's like a rate of change, more like. So it's like it's kind of spreading out the change of f along x. So it's like kind of the average change, the average amount of the f changes when along with respect to x, along the interval of size delta x. So for example, if, say like if delta x had changed by an amount of 1, this like what is like 1 feet. Oops, let's put it here. And the corresponding value for delta f, the amount that delta f changes, had been 2 feet. Or let's do it with 2 and 4. And the corresponding value for delta f had been 4 feet. Then the average like amount that delta f change, like or the speed, kind of like the rate at which delta f change, right, would be equal to 2. So right, because this is roughly saying that if this ratio is 2, this is saying that delta f is kind of changing twice as fast as delta x, right? Is that making sense? Maybe I should stop here first. So again, in this ratio, if the ratio happens to be 2, it's just saying that delta f is growing twice as fast as delta x. So on average, like the average change of delta f with respect to delta x is 2. So if you go back to the limit definition, each of these ratios is kind of like an average change or a rate of change. And so in the limit, you kind of interpret this as an instantaneous rate of change of f with respect to x. So this is kind of like an instantaneous. So in general, in this case, it's better to use this other notation for the derivative. When you write something like df dx, what that is telling you, because this notation is better just because it reminds you of a ratio. What this says is kind of like how fast the rate at which so for example, let me start giving you some examples to make this more clear. So let's say you had a rectangle. Let's say you have a rectangle of height 3 feet and variable width of size x. So the rectangle could look something like this. So this is 3 feet. And length, let's call it. Okay, so let me color this side with use a different color for the last side actually. So if you think of this last side of the rectangle as like some sort of sliding wall, right? As you move it, that will change the area of the rectangle, right? So the area of this rectangle, let's call it A. Is just 3 times x, right? It's height times length, right? So dA dx, right? What is this? What does this represent? It represents how fast, right? How fast the area is changing as you vary x. Oh, in this case, it's an easy derivative to find. That's just 3. Okay, but that's saying that. So what this is saying is that you know, with respect to x, I mean, it's better to actually this is actually better to interpret by multiplying both sides of the equation by dx. It's actually more convenient in this way because it is saying that if you change the length of the rectangle by some amount, which we're calling dx, by a tiny amount, then the formula for the area change, like the value of the area will change by a corresponding amount equal to 3dx. Is that making sense? So say, for example, if the x had been like 0.1 feet, right? If you had changed this side by 0.1, the value for the area would have changed by 0.3 because that's 3 times 0.1. So in a sense, like the amount that the area changes by is 3 times the amount that x changes by. Is that making sense? Any questions about this? So another example, of this is like a population growth. That's very common interpretation of this stuff involving derivatives. It's better for these problems to think about like you're dealing with something with like bacteria or viruses, something that reproduces very quickly. So imagine you have like a petri dish with bacteria or something that is changing over time. And in general, you wouldn't expect the number of bacteria to remain constant. Some will reproduce, others at the same time will be dying. Depends on how many resources are available to them to see whether it's the number of is increasing or decreasing. But then it does make sense to think that the population is a function of time. So this is like the number of bacteria at a given time. So for example, P of 3 could be the number of bacteria. Let's say that's 10,000. Well, in fact, that's a very small number because usually there are millions. But let's say 10,000, that could be like 10,000 bacteria at 3 hours, right? So this is 10,000 bacteria at 3 hours. Or whatever unit, 3 days, like 3 hours after you started counting, you set the timer on 0, 3 hours later, you have 10,000 bacteria. That making sense? And maybe P05 would be like, 20,000 or more, like, again, it depends on many factors. But so this is a quantity that changes over time, right? So because here T, I should have said T is the time at time T. So T is being interpreted here. Usually when you think of time, you call the variable T instead of X. That's less confusing. So dp dt, right, is a derivative of the population with respect to time, right? So it's the instantaneous change rate of change of the population size with respect to time. So for example, if dp if oops, if this derivative, I don't know how I can eliminate let me get out of this. Okay. So let's say if like let's say that at 3 hours, let's say that you know that the value for this derivative at when the time is 3 hours is positive, right? What did it mean that the derivative is positive? That means that the population at at 3 hours is increasing, right? The population at 3 hours is increasing. Because if you remember, as I had mentioned at the beginning of today's class, when the derivative is positive, that means that the function is increasing. The function here is the population. So that means that there are more members being added to the population. Like that, you could still have some bacteria dying, but it just means that at that instant, there are more being born, for example, than dying. Is that making sense? And then, like maybe, usually what happens in these biological things is that if the population just keeps growing and growing, eventually it just reaches like a maximum value and then it starts collapsing. So maybe after 5 hours, like there's scarce resources and more members start dying. So in this case, the derivative should be negative, um, because you're losing members, right? Is that making sense? And then the kind of like the other usual example that's very classical, which is one of the main motivations for why calculus was developed, was like in these physics problems about finding like of what velocity is, for example. So this other example comes from physics. So let's say you have like a road. So let's say the road is aligned with the x-axis, right? So like, I mean, if you're driving along this road, yeah, of course it makes sense to think that your position is changing over time, right? So x of t would be the position of the car at time t. So again, in this case, it's more natural to think of the position as a function of time, okay? And so dx dt, right, would be the rate of change of position like the instantaneous change of position with respect to time. And the interpretation of that, this is okay. So again, this derivative is telling you how fast the position of the car is changing over time. So that is what you interpret as the velocity of the car, right? So the derivative of the position with respect to time would be the velocity of the car. So x could be, here x could be 0 miles, here x could be 10 miles. Let me see here, x could be negative 10 miles. But that just means that, that just means that with respect to the origin, to what you chose to be your the origin along the x-axis, like this is 10 miles to the left. But so what happens if the derivative were positive? What would you say? What would you say about this car? Is it moving to the right or to the left? It's moving to the right because if you look at x is increasing as you move to the right in this diagram. So car is moving to the right. It's moving to the right. And what if dx dt were negative, right? Again, if the derivative is negative, oops, I keep writing this. If the derivative is negative, that means that your function is decreasing, right? What does it mean for the function x to be decreasing? That means that the values for x are getting smaller. So in which direction the values of x are getting smaller? To the left. So that actually means that the car kind of changes direction, changes its mind with respect to this diagram. And so now the car is moving to the left. Is that making sense? Any questions about this up to this point? Okay, so in related rate problems, so what is a related rate problem? Just like again, it's not a new technique. It's just like an application of how we have been finding derivatives. So it's a way to apply derivatives. It's just like the applying the derivative rules that we know to solve applied problems. So in these related rate problems, it is just about conceptualizing this stuff. So let me just check where I have these written down. Here it is. Oh, by the way, before I write it down, like just another last thing a useful thing to have is like if you give in many applied problems, the units you work with, I mean, the quantities you work with have units. So the units of a derivative are the units of f divided by the unit of x. So that's a useful thing to know. You'll see it you'll see it in a moment once we start doing some applications, but it's kind of like a useful thing to keep in mind. That's also why it's useful to have the derivative written as a ratio. I mean, this notation for the derivative is convenient because it looks like a ratio, and that's useful because of that. Okay, so yeah, I'm about to do some examples about these related rates, and so let's take a 5-minute break. Let's meet at 1:45 again if you need to go to the bathroom, so I can start doing some examples about this. I'll show you what the strategy is like usually. And resume the recording. So I'll start with an easy example of related rates, and we can do some more complicated in a moment. Is increasing at a rate of 2 centimeters per second, and is three centimeters per second. Is the area on the rectangle changing? Let's call it okay. Okay, let's try to think about what this problem is saying. Again, you'll see that we are not going to use anything weird in terms of derivatives. It's more like interpreting correctly the stuff that we already know how to work with. So in this case, we're dealing with a rectangle, right? So the first thing you should do is to draw like some sort of diagram of the situation. So we have a rectangle. You can call it x and y, the variable, the size of the rectangle. Okay, and it says that the height, right? Now, once after drawing the picture, you should start interpreting the variables, right? So the height is increasing at a rate of 2 centimeters per second. Okay, so if you think about that, that is first it has the magic word rate, right? And so that should suggest a derivative, right? And so and moreover, it like the rate that is given to you is has some units, as I was saying, right? Which are like the units. The numerator has units of length, and the denominator has units of time, right? Seconds is in time. So that suggests that it is like telling you how fast the height is changing with respect to time. Is that making sense? So that is saying that the derivative of y with respect to time is 2 centimeters per second. Is that making sense? This is the most important thing, actually. Are there any questions about this? Just to kind of translate what the problem is saying into like something in terms of a derivative. Is that making sense? Okay, let's see if this is actually making sense. So then it's saying that the length is decreasing at a rate of 3 centimeters per second. So how should I interpret that in terms of a derivative? What should I write? What derivative should I write? Good, so it should be dx dt, and that's the important thing. It should be minus 3 centimeters per second. The minus coming from the fact that the length is decreasing. So the minus with a minus sign, since the length is decreasing. Is that making sense? Actually, that's another of the tricky parts of these problems, where sometimes that the number or the rate that you're given is just it looks like positive, but it has like a word in front of it that's supposed to remind you of it being like negative number. Is that making sense? So don't fall for the trap where the sign is kind of being implicitly determined by the word in front of the rate. Is that okay? Any questions about that? So there, what is this asking? The problem is asking for the rate of the area, right? So the ADT is what the problem is asking for. Okay, but what's the area of a rectangle? It's just length times height, or x times y. So what is the ADT? That just means the derivative of a with respect to t. So what you should do in these problems is just take the derivative on both sides with respect to the variable that you're interested in. Here it's like the variable that you care about is the time variable. Okay. And then how can you find this derivative? What is that equal to? What can you do to find this derivative? Yeah, you should do the product rule because you have to think in, that's what can be confusing also about these problems. You have to think in these problems that both x and y are functions of time because both of them are changing over time at a certain rate. So actually time is kind of like, it's not even appearing in the formula, but it is kind of like the stuff, the variable with respect to which everything else is changing. So you have to use a product rule, good. But once you get to this point, it is more or less substitution. If you do things correctly, once you reach this point, it's just like a bunch of substitutions. So what is the XDT? We had said that the XDT was minus 3 centimeters per second, right? What is Y? Well, Y, they say Y, the height is 4 centimeters, right? We want this value when the height is 4. And then what is X? X was the length equals 5 centimeters. And the YDT was 2 centimeters per second. Okay, so this gives you minus 12 centimeters squared per second plus 10 centimeters squared per second. And what is that? That is minus 2 centimeters squared per second. Is that making sense? So notice, like this is in these types of problems, applied problems, that's why it's important or useful to keep track of the units, because area has units of length squared, right? So if we are measuring the length in centimeters, for example, that's why we are getting centimeters squared. And dt, I mean, time has units of, like, for example, seconds. So centimeters squared per second makes sense as a as the correct units for this rate. Is that okay? Yes, there will be a related rate problem on the exam, correct? Yes. So you see, like in terms of the calculus involved, it is not too bad. It was just applying the product rule. It's more like like what makes these problems more or less interesting is to translate the statement of the problem into like actual uh, mathematics quantities. Okay, let's do another example. Unless there are other questions about this one. Um, okay. Let me find another interesting example. Oh, the other thing I was going to say is that, yeah, let's do the weather balloon. The other thing I was going to say is that because this the derivative was negative, that means that the rectangle is shrinking, right? Means that you're losing area, so the rectangle is becoming smaller. Okay, let me give you another problem which is kind of fun. Let me copy it first. So here's another example. A weather balloon. Twelve meters away from the launch point is being pointed at the balloon at all times. But also, these are kind of like this type of problems which are kind of very long word and very worded. So that's why sometimes they're called like word problems because just the description of the problem is kind of takes a little bit to describe completely. So they're kind of like these word problems of calculus. So the weather balloon is rising at 6 meters per second. I'll let you copy this first. At what rate is the camera's tilt changing in radians per second when the balloon is 5 meters off the ground. And I'm about to show you an animation in a second also. But let me give you a second. let, let you write this first because it takes a little bit of time to even write it down. Did everyone have a chance to copy this? So let me show you an animation. Let's see if it works. Okay, I have to go to my website. I think it's this one. So you see, this is the weather balloon. It's rising. Okay, this is a camera that's located 12 meters from where the balloon starts rising. And you see, like the camera is following the balloon, so the angle is changing as the balloon rises. Is that making sense? So we want to find out how fast this angle is changing, basically. Is the animation kind of clear? So like again, it is like like the point of these problems is not that the the calculus is too complicated. It's more like the translation of the problem into the derivatives and all that stuff that requires some thinking. So let me draw that for you. So let's just, again, you must always basically do a diagram in every single one of these problems. You won't get that far if you don't have like a diagram. So let's just try to do something similar to the animation I showed you. So you have the place where the balloon is being launched. So let's try to draw something like this. Okay, so that's the balloon. In general, it will have some height y, and then there's like this camera, which is always located 12 meters from the launch side of the balloon. Okay, so this is where the camera is. And then there is a distance between the camera and the balloon right here. So there's this angle. And so let's just interpret this question. So it says, at what rate is the camera tilt changing? So the tilt has to do with the angle, right? So what the problem is asking is for d theta dt. So d theta dt is what the problem wants. Just noticing that is like an important thing. So understanding what the problem is asking for is important. So is that making sense with everyone? Why is that what we're trying to find? It also helps the fact that it's giving you the units. So it's telling you that this rate should be in radians per second. Radians is units of an angle, and seconds is units of time. So that also suggests that what you're trying to find is a derivative of theta with respect to time. Is that okay? Now, okay, here's where we need to start reading the problem to see if we can find something else. We already used the fact that the camera is 12 meters away from the launch point, right? That is already incorporated into the diagram. Now the weather balloon is rising at 6 meters per second. We haven't used that. So how could I use this for something useful? What can I say? What does that mean? Yeah, perfect. Excellent. And again, this is important. This makes sense because y, which is the height of the balloon, is in units of meters, t is in seconds. So the derivative should have units of meters per second. So this matches this has the correct units. And again, thinking in terms of the units is very useful in this problem. Okay, so basically we have information about the derivative of y, right? But we want information about the derivative of theta, right? So the question is there a way from this diagram to relate theta with y? That's kind of what we need to do because like the information that the problem provides for us is in terms of y. So we have to relate y to theta to turn it into something useful. So can you think of this diagram as telling you something, some connection between theta and y? Yeah, excellent. Yeah, so it is like the easiest thing to try here is like the trig functions. So to relate theta to y, you could have gone either with the sine, but the sine requires using the hypotenuse, and we don't have like a specific value for the hypotenuse, so that's not that useful. But the tangent involves y, the opposite side, and the adjacent side, and we do know something about the adjacent side because it's always 12. So the tangent of theta, perfect. Tangent of theta is y over 12. And that's the key equation. That's the equation that will make everything else work. So finding this out is kind of useful as well. That making sense? Once you have like this equation that relates theta with y, you can take the derivative of both sides of the equation. So you can take the derivative of both sides of the equation with respect to time, right? That's the important thing. So let's start with the easier one. What's this derivative? The 12 can come outside the derivative because it's a number. So you can write this as 112 dy dt. Which is great because we already had dy dt before, right? So this is easy to study. This one, we have to think a little bit more. So what can you do with this one? What is this equal to? Is there a way to simplify this derivative? Or is there a formula for the, yeah, there is a formula for the value of the derivative of tangent, which is secant, but you have to be careful because that's a derivative of tangent with respect to theta, not t. So the trick, what's the trick is to use the chain rule. You see? So we don't know the value of the derivative of tangent with respect to t, but we do know the value for the derivative of tangent with respect to theta, because that's just secant squared. So, but there's no theta in the derivative, so you multiply and divide by d theta, okay? And so that gives you secant squared of theta times d dt. Sorry, d theta dt. And I should put here that this is 1/12 meters, maybe. Meters. And what is dy dt? Dy dt is 6 meters per second. Is that making sense? Any questions about this? But what is, I mean, from here you can kind of solve for d theta dt. And so what does that give you? 6/12, that's 1/2. You can keep the units if you want, so you can keep seconds. And then, you can also divide you can divide both sides by secant squared, so you can put secant squared here. But I don't know if you remember, 1/secant, I mean, is cosine, basically. So the theta dt is cosine square over 2 seconds. Is that making sense? But we want this value when we want this value when the balloon is 5 meters off the ground. We want this when balloon is 5 meters off the ground. So again, if you draw the diagram here, you get this, right? So what's the value for theta? Oops. what's the value for theta here? Well, remember the hypotenuse, if you use Pythagoras theorem, would be the square root of 12 squared, which is 144, plus 5 squared, which is 25. So what is that? The square root of 169? And that should be 13, I believe. So the cosine of theta in this case is 5/13. So the theta dt would be cosine squared, which is 25 over 169 times 1/2 seconds. Well, I would give you better numbers on the exam, so that but I mean smaller numbers. But that's kind of like the idea. Is that making sense? Are there any questions about this? Let's see. I think we have time we should do another problem about this. Okay, let's see if I have one that I want to do. Okay, let's do this one, which is actually similar to one that you have on your MyLab assignment once you check these problems out. So I just don't like them. I'll try to change the numbers, okay, to make them smaller. Or well, maybe that doesn't matter. I can use these numbers, I suppose. Is leaning against a house. Well, let's do it against a tree. When the base starts to side away, by the time the base is 7 feet from the tree, the base is moving away at a rate. Of 722 feet per second. What is the rate of change of the height at the top of the ladder? Or how fast is the top of the ladder falling down? Let me ask it that way. Okay, so let me give you like, let's, I think it's useful for you to take a couple minutes to try, think about it on your own before discussing it. So let's maybe take 4 or 5 minutes for you to try to draw your own diagram, and then we'll do it together. But I think it's useful for you to just give it some thoughts first. Okay, so yeah, let's meet like in 5 minutes to, and we'll solve it together, if that sounds good. Okay, hopefully you had a chance to think about it. So let's do a diagram. So here's the tree. Here's a ladder. In fact, I'll do it a little bit larger, longer. Okay. It's actually better. I mean, well, it's fine this way. Okay, so 25 feet ladder. What is 25 feet? The the length of the ladder. So like this purple thing, right? This is 25 feet. Okay, and then in this problem, so what is the base? The base is here, right? So that's telling you that that is moving at a rate of 70 feet per second, right? So we need something that keeps track of the base. The easiest thing to call that is x. So let's call this x, right? So x is like the position of the base. Is that making sense? So it's saying that the base is moving away. It's moving away from the tree, so it's moving it to the right. Since it's moving to the right, this rate of change is positive. So it's saying that that rate of change is 72 feet per second when you are 7 feet away from the tree. Is that okay? Questions up to this point? And then it's asking for, what is it asking for? It's asking for how fast is the top of the ladder falling. So here you have the top of the ladder, right? So there, right, this keeps track of the top of the ladder. And so position on the top of the ladder. So it wants what? It wants us to find dy dt. Is that making sense? Are there any questions about this? Again, there's a very similar problem to this one on the MyLab assignment. Once you start working it out. So now, again, we want dy dt. We do have the x dt, right? So we need an equation that relates x and y. So based on this diagram, what's an equation that we have that relates x to y? Any ideas? Uh, I mean, you could use the tangent, that's fine, it's just that the tangent, then, you know, the angle theta kind of, we don't know much about the angle, so it is more convenient to, you know, there's nothing in the problem that gives information about the angle, so we then need to try to figure it out on our own. But there's actually something more clear in this diagram that relates x to y directly. I'm kind of coloring for you. Yeah, the Pythagoras theorem, good. So you do know that 25 squared, right? By Pythagoras, 25 squared equals x squared plus y squared. And there you go. I mean, and this is the key. So again, in all these problems are really great. The key is always to find like something that relates the variables that were given to you in the problem. What you can do next is take the derivative of both sides of the equation with respect to time. Okay. The derivative, this is just, I mean, you could compute 25 squared if you want. It's not necessary because it's a derivative of a constant. Remember, the derivative of a constant is always zero. And then the thing that you have to find is these two derivatives. Okay. What can you do to find these two derivatives? Yeah, you should get used to this. Like it's more always like some sort of like chain rule problem. So, but you apply the chain rule with respect to whatever you find useful. So what's useful here is to take the derivative with respect to x. So you kind of, that's why I'm multiplying and dividing by the x. And here, what's useful is to take the derivative with respect to y. And so that's why I'm multiplying and dividing by y. So, and what's the derivative of x squared? That's just 2x. So you get 2x dx dt. And what's the derivative of y squared? That's 2y. So you get 2y dy dt. Is that making sense? And again, you want this, we want this when the base is 7 feet from the feet 7 feet from the tree. So you should do a diagram here, or here x is 7 feet. The ladder is always 25 feet. And so what would be the value for, oops, here, let me change the colors. What would be the value for y? Well, again, you kind of have to use Pythagoras theorem again. So the value for y would be the square root of 25 squared minus 7 squared. And well, you have to do that. I mean, again, I will give you smaller numbers on the exam so that it's easier to take the square roots. It should be the square root of 576, which I don't know if that one, but let's see, is that one no, I don't think that one has like a actual useful square root to work with, or does it? Mm. Oh, sorry, I did it wrong. No, this is okay. Yeah, I don't think there's like a good square root for, I mean, you would need to leave it like that. Oh, is it 24? Okay, I do promise to give you numbers that are, yes, good. But again, that's not something that at the top of your head you should would expect you to know. So like the numbers always will be smaller, the ones that I will give you on the exam. So that's for taking square roots and things like that is easier. But good, that's useful. So 0 would be 2x, but x is 7 feet. And what was the x dt? The x dt was 72 feet per second. Plus 2y, but y is 24 feet. And dy dt, we don't know. That's what we're trying to solve for, right? I mean, so you can divide by 2 on both sides of the equation, and so you get 7 feet times 72 feet per second plus 24. Oh, okay, you can even divide by 24 on both sides. I mean, you have to do some simplification here. Again, my point wouldn't be to kind of like have you spend too much time on simplifying these numbers, but you're right, 24 times 72 is 24 times 3, so you would get 21 feet squared divided by second over seconds plus and you can also cancel some feet dy dt. Yeah, so I'm dividing by 48 on both sides of the equation, basically, to get that. And again, like the numbers will be smaller on the problems I actually end up giving you. So this would be minus 21 feet, minus 21 feet per second. The important thing was kind of to realize, the important thing about this problem was to realize that you could use Pythagoras theorem to relate the variables, basically. Is that making sense? So again, like the takeaway hopefully is like the problems themselves do not require like crazy derivatives. So the difficulty of these problems is not in finding the derivatives. It's more like in setting up an equation that's useful to find to take the derivative of. So in all these word problems with related rates, the derivatives will always be simple. It's more like what's the equation I should use that relates the variable so that I can find the derivative that I care. So that is not like that's not something you can tell ahead of time so easily. So this is why you have to do like a couple of examples of related rates to kind of get like a feel for what sort of like equations you should use. Typically, it's like Pythagoras theorem, like this one, or something like tangent, sine, or cosine, like the previous example. Um, like and like geometric formulas, like the area of a rectangle, the area of a circle, things like that. But it's not like it's like the kind of like the interesting part of these problems is to decide what's the equation you have to use and how to interpret everything in the problem. Okay, so but I think okay, so yeah, this was the last topic for the exam. It's a good place to end. So I'll send you in a couple of minutes like the announcement with the information for tomorrow's quiz and yeah, and I'll in a couple of hours I'll send you like a study guide for the exam and some practice exams. But I'll so tomorrow we'll do something different. So, that sounds good. But yeah, it will be the same format. I'll specify that on the study guide for the exam, but it will be the same idea.